Okay, so this is chapter 4.7, day 2, graphing linear functions. So we're going to take function notation a step further today. We're going to graph the function and compare it to the parent function. Okay, so I guess I should have hid that. The parent function for all linear equations is the most basic linear equation. And this is given to you here. So the most basic linear equation is f of x equals x. And so as Kyle just said, we could change f of x to what letter? Y. We could say y equals x. That's the most basic line. And when we look at that, we don't see as much in it, do we? I mean, we just see two letters, really. But if we were to reveal the hidden things and put this into slope-intercept form, what would the slope of this be? What's the number here? 1x. And then what would the y-intercept be? Plus 0. Good. So here we have slope-intercept form. So we can identify the slope. The slope of this equation is 1, and the y-intercept is 0. So when we graph the parent function, we start at the point of origin, and we can use the slope to move up 1 over 1, up 1 over 1. We could also go down 1 and to the left 1. And so we have the parent function. So we will be asked to compare our functions today with this, the most basic linear function. When we graph a new function, how does it compare to this function? Okay, so let's compare this parent function to some other basic function. G of x equals 2x. G of x equals 2x. Okay, so just as we did with the parent function, we could change this function from function notation to slope-intercept, right? So Sabrina, what would this function be in slope-intercept?
Y equals 2x plus 0.
And you can put the plus 0, which is invisible, but it's useful to understand where we're starting. So we're starting at the y-intercept, right? The y-intercept of 0. So we start at the point of origin. And our slope is, give me both values, the rise and the run. The slope is
2.
Good. Slope equals 2 over 1. Okay? So we're going to start at the starting point, our y-intercept, and go up 2 over 1, up 2 over 1. This also equals negative 2 rise over negative 1, right? That's still 2, so we could go down 2 and to the left 1, down 2 and to the left 1. So we have the new equation. I'm putting the name of it up just at the tip of the arrow, that's G. The original parent function, we had the function notation of f, we're calling that f. So now we can see which is which, right? So now, when we compare these functions, which is what we're going to do today, there are two pieces to the function that we talk about when we use this form for graphing, right? So what are the two parts of the function? We have, what form did we say this is? Slope-intercept, right? So the two parts are slope and intercept. So we're going to compare those. Compare M and B, okay? So let's start with the easier one, I think, here is B, which is your y-intercept. How do the y-intercepts compare in this set of equations here, set of functions? Madeline? They're the same. They're the same. They both have 0, 0, the point of origin, as their y-intercept. What do we call graphs that cross through 0, 0? There's a special name for these. They are? These are lines. They're all linear, and they pass through 0, 0, so they are? I think I heard it. Direct variation. There it is. So these are both direct variation. Okay, you could write that whole thing out if you want. Okay, the other thing we compare is slope. Are the slopes the same here? No, these are different. Okay, these are different. And so what happened when we move from the parent function, the red one, to the blue function. Did we get flatter or steeper? Steeper, okay? So when we get steeper, there's a name for that transformation. Do you remember what we said yesterday? Is it a vertical stretch or shrink?
Stretch.
Good, it's a vertical stretch. So the new function, g of x, is a vertical stretch of the parent. And we could say by a factor of, what is the factor we multiplied g by? 2. So it's by a factor of 2. Okay? Okay, so example B, let's compare the function h of x equals negative 1/2 x to the parent function. So you may need to pause the video, but we're going to go ahead and draw in the parent function. I'm going to make sure I have a blue line. And so the parent function has a slope of 1 and travels through the point of origin. Okay, so now h of x. So we said we could, in order to graph it, put it into slope-intercept form. So Haley put it in slope-intercept form.
Y equals 1/2 x plus 0.
X plus 0. Okay, negative 1/2 x plus 0. So Haley, the slope is?
Negative 1/2.
And the y-intercept is?
0.
0. So we're going to start where?
A 0.
At 0, 0. Place a starting point there. That's our y-intercept, right? And then we're going to move where?
Up 1 over, or negative 1 over 2.
Negative 1 with a positive 2. We could also say that this equals positive 1 as long as we go negative 2. Rise of positive 1, negative 2, run. So there we go. Okay, so now let's compare the functions. And again, we're comparing m and b. So when it comes to our y-intercept here, is there a difference? No difference again. No difference. They both are at the point of origin, though. So we could say that they're both what type of equation? Direct variation. Okay? But when it comes to the slope, we have some differences, don't we? Who can name one of the differences? Madeline. Okay, she says, and she has it right, it's a vertical shrink. And so what is the factor that caused the line to move away from the y-axis? By a factor of negative 1/2, right? That's what we're multiplying by. So when we multiply by a fraction, the half is causing it to move away from the y-axis. But we also have a drastic difference from this positive slope to a negative slope. So how can we describe that kind of change when you go from one side to the other side? It's a what? It's a, I hear one person. It's a reflection, right? Just like a mirror, it's a reflection in the y-axis. Okay, so you will definitely need to pause the video and draw these 3 coordinate planes showing the parent function in one color. And on my example, the parent functions are in blue. And then show the transformed functions in a different color so that we can talk about what went on to transform the parent to these other functions. So pause the video and come back. Okay, so let's compare the transformed red function with the parent function, which is a blue. So in this first example, when we compare, what are the 2 things we're comparing again? We're comparing, I hear one person saying it, we're comparing the slope and the y-intercept. Everybody say that? We're comparing
Slope and y-intercept.
Okay, so let's start with y-intercept. So, is the y-intercept the same in the transformed function for the first graph? No, these are different. Different y-intercepts. So that's interesting. What happened if we believe that the parent has become this other function? What happened with the y-intercept here? What happened? It went which direction? Did the y-intercept go? It went up, right? We see that this is the red line has a y-intercept at, it looks like 4, and the original parent was at 0, right? So we've gone up, okay? Interesting. How about the slope? Is the slope different? No change. So if we have no change in the slope, but they have different y-intercepts, what can we say about these two lines? Good, they're parallel. Parallel lines. That's your symbol for parallel. Okay, so what is the transformation that moves a line just up? This is different than the previous two functions we just graphed. This is the fourth transformation I said we would have. So what happens, we didn't spin it around or reflect it or anything, we just moved it up. Huh? Very good. This is a translation. And so remember, the SL reminds us it's a slide. It's a slide, and in this case, this is a translation up. Okay, a vertical translation in a positive direction, adding 4. We added 4. Okay, in the second graph, let's compare the y-intercepts. So, are the y-intercepts different? No difference. So this is different. No different. So this is like the previous two graphs we just did, and because they all have a y-intercept at 0, 0, these are all what type? Good, direct variation. Direct variation. Okay, when it comes to the slope, though, we do see some differences, and that's why you see 2 red lines. So could we say that these slopes are all negative? Could we say that they're all positive? So imagine the ant walking on a line, positive and positive. They're both positive, but one of them is different than the other, right? So how would we describe this function here compared to the parent? This function is a vertical stretch. So we have vertical stretch when your slope is greater than what? What's the slope of the parent? We said the slope of the parent function is? 1. We said 1. So if I have a stretch, the slope is greater than 1. Greater than 1. Okay? And then in the other case, here, this flatter line, we have a vertical what? Shrink. And so in this case, the slope is not negative. So let's say the slope is greater than 0, but it is less than 1. So it's some fraction between 0 and 1. This could be 1/3. As a matter of fact, it looks like 1/3, up 1 over 3. Okay, 1/3, it could be 1/2, whatever. It's just not 1. It's less than 1. Okay? And finally, we have the last one, right? So what is different? Are the y-intercepts different? No. So these are both direct variation, or all 3 are direct variation, because there's no difference here. But when it comes to the slope, we have a drastic difference, right? What's different? Negative. Okay, so what do we call that transformation when we have a negative slope? It went from positive to negative. That's a good reflection. And do we also have the possibility of stretches and shrinks here? Yes. So we could have a vertical stretch or vertical shrink, depending on the factor that goes along with the negative slope. Okay, we only have 30 seconds left, and your assignment is here. And I'm passing back the quiz today, so bring that back tomorrow.